Hello, everyone. Thank you for attending the final presentation of my project titled Modeling and Characterization of Acoustically Absorbing Liners. This project is carried out at the Technical University of Munich, Chair of Thermodynamics. In this presentation, after recalling the motivation and objectives of the project, relevant theoretical background is briefly described. Then, modeling approach will be explained, followed by the numerical analysis. Finally, an overview of the results will be presented, followed by the summary and outlook of the project. Combustion instabilities may lead to structural damages to the combustor or flame blow-off. One method to avoid these instabilities is increasing the acoustic losses of the system by damping acoustic pressure pulsations. In this project, perforated liners are focused as acoustic absorber. To predict the behavior of perforated liners in damping acoustic pulsations, several impedance models are proposed and available in the literature. In practice, orifices are closely distributed, such that the interaction between acoustic radiations from neighboring orifices can affect their acoustical behavior. However, most of the models neglect the interaction effect between the holes. The hole-to-hole interaction effect may change the resonance frequency of the resonator due to the non-planar wave creation in the cavity, the orifices in the perforated plate, and in the near wall region in the combustor. Considering this effect may help to predict the resonance frequency of the resonator accurately. The goal of this project is acoustic modeling and characterization of perforated liners. For modeling part, the effect of hole-to-hole interaction is modeled analytically and analyzed numerically. For characterization, the acoustic behavior of perforated plates focusing on the hole-to-hole interaction effect is experimentally investigated. What is end correction? At low frequencies, on-the-plane waves can continuously propagate in a uniform dot, so the plane wave theory is fully sufficient. However, at the area jump, evanescent nonplanar waves are created. The effect of these nonplanar waves can be integrated into the plane wave analysis by using an equivalent acoustic impedance at the area jump, or can be called additional length or end correction. Here is denoted as L prime. Several authors studied acoustic radiation theoretically and experimentally and proposed expressions for the end correction. The effect of orifice radius is considered in several previous studies, but these expressions do not consider the effect of orifice spacing and therefore inappropriately used in impedance models to account for the hole-to-hole interaction effect. For two plates with the same orifice radius and different orifice spacings, the acoustic velocity magnitude in the vicinity of orifices is shown. When the orifices are distantly spaced, as shown in the figure on the right, each hole's acoustic radiation might be only slightly affected by the neighboring holes. When the orifices are close to each other, as shown in the figure on the left, the acoustic radiation of holes is strongly affected by each other. The region with oscillating mass extends on both sides of the orifice. The acoustic velocity does not diminish so rapidly due to the combined momentum of the interacting jet flows from neighboring holes. The theoretical studies are limited to the two-hole configuration, where only two orifices are placed on a plate. Therefore, it's necessary to theoretically investigate the multi-orifice configuration. In order to investigate acoustic propagation through small orifices in a multi-orifice configuration, wave equation is solved in the domain composed of a perforated plate and a cavity. In this schematic view, R0 stands for the orifice radius, RC is the cavity radius, LC is the cavity depth, and LP is the thickness of the plate. General solution of the pressure in the cavity and orifice is presented. By imposing boundary conditions and forming a matrix set of equations containing the description of boundary conditions, solution of the acoustic field inside the domain can be determined. By solving equations for a number of higher order modes, M and N, pressure amplitudes for waves A, B, C, D can be acquired. Normalized end correction is defined as an additional impedance. Here, subscript 00 stands for fundamental mode. Several perforated plates with different orifice radius and spacing were studied for the triangular, square, and rectangular patterns. As shown in this figure, triangular configuration denoted with P, S stands for square pattern, and SA for rectangular. The range of orifice radius and center-to-center distances are presented in this table, and number of cases for each configuration, which were studied analytically by this method. To investigate the hole-to-hole interaction effect, wave equation excluding viscous and thermal losses is solved in frequency domain based on finite element method. The three-dimensional computational domain is similar to the impedance tube used in experiments. The excitation is applied at the inlet. The maximum absorption of resonator happens at the frequency where the acoustic reactance is zero, or where the pressure and velocity are exactly in phase. This frequency coincides with the resonance frequency of the resonator. End correction is calculated by having frequency, resonance frequency, A, which is the sum of open area, V is the cavity volume, and LP prime is the length of orifice, which is the thickness of the plate, plus the end correction. By having all the parameters, the unknown is end correction and can be calculated. Similar configurations to the modeling section are studied using FEM. In this figure, the normalized specific acoustic reactance of several plates obtained using FEM are presented. As it is shown here, by keeping the orifice radius constant and increasing the distance between the orifices, acoustic reactance curves shift to higher frequencies. This increase in resonance frequency implies that the end correction decreases by increasing the orifice's spacing, according to this equation for resonance frequency. Similar behavior observed for all the studied cases. The normalized end correction for all perforated plates in the ranges listed in the table are obtained from FEM and presented for P and S patterns in these figures. Results show that decreasing the distance of orifices increases the normalized end correction, and vice versa. Additionally, increasing the orifice radius increases the end correction. Normalized end correction behavior may be related to the distance and the radius of the orifice. Therefore, a model is fitted to the results of the P and S patterns separately. In the results section, first we have a look at the configurations studied experimentally, then measurements without airflow, followed by the model's prediction, and measurements with airflow followed by models prediction. These are the configurations perforated plates studied experimentally. For each configuration, triangular, square, and rectangular, the orifice radius is kept constant and the center-to-center distance is changed. Therefore, the overall porosity, the open area ratio, is kept constant. This is similar for all the cases investigated. In the absence of airflow, reflection coefficient of perforated plates is acquired. Results show that the resonance frequency shifts to lower frequencies as the holes approach each other. This implies an increase in the end correction, as all the geometrical parameters are kept constant except orifice spacing. The square and rectangular patterns show similar behavior. Bellucci model used as impedance model. The reason for higher frequency is that end correction model used by Bellucci is developed for a single orifice and neglects hole-to-hole interaction effect. The 3D analytical method significantly improves the prediction of resonance frequency. Slight deviation may be associated with the number of higher order modes M and N considered to obtain the end correction. A similar behavior is observed for S1 case. To present the general influence of bias flow on the damping behavior of the perforated plates, considering hole-to-hole interaction effect, P1 and P3 configurations are selected. Introducing flow and increasing its velocity shifts maximum absorption to higher frequencies. Maximum level of absorption reduced while the absorption becomes broadband. Similar behavior is observed for P3 case. However, the difference in resonance frequency between P1 and P3 cases can be noticed for each mass flow rate. Comparing P1 and P3, Bellucci model predicts the resonance frequency of P3 accurately, while for P1 is far from experiments. Indeed, Bellucci model gives a similar resonance frequency for P1 and P3 because that model cannot differentiate these two cases and treats them in a similar manner. The reason is that in Bellucci's model, the hole-to-hole interaction is not considered appropriately. The present model can predict the resonance frequency of both configurations and for different mass flow rates accurately as shown in the figure. To summarize the outcomes of this project, a 3D analytical method is developed to investigate the hole-to-hole interaction effect by considering the non-planar wave propagation at the orifice plate area jump. The hole-to-hole interaction effect for a series of perforated plates is studied using FEM, and a model for prediction of normalized end correction of multi-orifice perforated plates was proposed. Several perforated plates were investigated experimentally. Results showed that the resonance frequency is sensitive to the hole-to-hole interaction effect. The obtained model for normalized end correction was integrated into the Bellucci impedance model and compared with the results of 3D analytical model and measurements. Also, one paper was submitted to ASME Turbo Expo 2021, and the title was Influence of Hole-to-Hole Interaction on the Acoustic Behavior of Multi-Orifice Perforated Plates. It received 3 recommendations for journals, and the results will be out in 2 weeks. According to the latest progress report in August 2020, the project timeline is presented as follows. The main work packages are acoustic characterization of perforated plates, acoustic impedance modeling, and acoustic damping rate measurements for reacting condition. For the last work package, there was a modification which was approved by my supervisor and communicated with the project coordinator. Additionally, I added another work package which includes the FEM analysis. Regarding the deliverables, the deliverable 3.2 submitted in August 2019, and the outstanding deliverables are first secondment report, which is done at GE in Munich, second secondment report, which was done at University of Twente, and project final report. And at the end, thank you so much for your attention.